All right, my friends, let's take a look at the dreaded potato problem from 2017. There we go. Now we're focusing. Okay. Anyway, I have to say there were quite a few jokes about this problem in 2017. People were pretty angry that, 12 years at least of studying mathematics in school, and it came down to the boiling potato problem. Anyway, so people were pretty upset, and then I think they're also just extra upset that that it was kind of hard. So there you go. Anyway, so basically, I'll just read it through, and then we'll get down to it. But I think that if you break it down step by step, it should make sense once we're done with it. But you'll definitely see why some people were pretty frustrated. Honestly, it came down to a lot of us being math jocks and really not liking to read very much, and possibly having some bad feelings about being asked about a boiled potato, but Anyway, so it says at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. The internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh dt equals negative 1/4 h minus 27, where h of t is measured in degrees Celsius, and this is very redundant, h of 0 is 91. Okay, so for part A, it says write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. So for part A, we're really just doing something that looks like algebra 1 here. Y minus y1 equals slope times x minus x1, except we wouldn't have an x minus x1. We'd kind of have like a t minus t1. Anyway, I would leave this as y. Some people might change it to h. That's not the end of the world, but I would probably leave that as y. Okay, so basically, here graphically speaking, we're just thinking here's time, here's the temperature of the potato in degrees Celsius. Your initial value is 91 degrees Celsius. Okay, 91, you know what I mean. Anyway, whatever the graph looks like, I don't know, whatever your h of t graph looks like, what's the equation of that tangent line right there. So we're going to need, so the initial point would be 0, 91. So you will see me putting a 0 here and a 91 here. And then as far as the slope goes, we are going to figure out what's the change in the temperature with respect to time at the point 0, 91. That's what we will put there. Okay, so most of our work in part A would just be to get this slope value. So the change in the temperature with respect to time at 0, 91, if you follow the rule here, it's in terms of h, so we'll just be putting 91 in for h and then evaluating. So this would be negative 1/4 times the quantity, whoops, what are we putting in for h? 91, okay. 91 minus 27. Okay, and then for me, one of the hardest things in this problem was the subtraction involved. 91 minus 27, I believe, is 64, and then negative 1/4 of that is negative 16. So my answer would just be this point slope form, or you could write it a little differently, but you could just do y minus 91 equals negative 16 times t minus 0. That is not exactly simplified, but it is, a correct answer. You could always simplify it, which helps you in the next step. Y is equal to 91 minus 16t. They're both correct answers, equally correct. One might look cuter to you, but they are equally correct. Okay, now it says use this equation to approximate the internal temperature of the potato at time t equals 3. So this is where the graph and the line equation are connected at 0, and you're going to go down the ways a little bit, and you're going to be plugging 3 in the idea is to plug it into the line graph instead of the actual function rule. So let's just do that. So your line graph, if you were to plug in 3, would just give you 91 minus 16 times 3. 16 times 3 is 48. 91 minus 48 ends up being 43. So I would say h of 3, it's not exactly what you'd get on the line graph, but we'd say 43 is an approximation. Might not be that great of an approximation, but it's an approximation. Okay. There's one thing that they were looking for, and then either of these beauties was the other thing that they were looking for in the problem. Okay. So that's part A. Part B is likely, if you had a question, part B is likely a reason why you had a question. So let's look at that. Part B says use basically the second derivative of h with respect to time to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. I'm going to end up redrawing a picture a little more carefully. This was just kind of a loose, I'm not thinking very hard sketch. So I'm actually, out of laziness, just going to erase what I have here. Okay. Okay, so first, let's figure out, what's this? Basic principle, it means you take ddt of dh dt, and then from there, that would be ddt of, and then dh dt is this beauty right here. So it's equal to negative 1/4 times the quantity h minus 27. Many ways to go about this derivative. You could distribute, or you could use properties of derivatives. Either way, you should end up with negative 1/4 times dh dt. Okay, and then now let's substitute what dh dt is. Dh dt again is negative 1/4 times the quantity h minus 27. So you have negative 1/4 times negative 1/4 times the quantity h minus 27. And then I'm just going to multiply the negative 1/4 together. That will serve my purpose pretty well. And then I would say that this is the second derivative of h with respect to time. And this is one thing that they would give you points for, since they specifically asked for it in the problem. Okay, now the other thing they asked you about was somehow we're supposed to be able to use what we got here to determine whether our answer in part A is an underestimate or an overestimate of the internal temperature. So let's think about this. What does a second derivative tell us about a graph of an original function? What does it tell us? It tells us a concavity. So if you look at this, this function, notice that, so you've got positive 1/16 times this factor, h minus 27. Well, 1/16 is positive. Let's think about h minus 27. As long as h is 27 or bigger, this is positive in here. So I could say this second derivative, whenever h is bigger than 27, is positive. I hope that makes sense. Again, I'll say it again. So if you're plugging a number in bigger than 27 here, that number minus 27 is positive, and you're multiplying it by a positive. So your second derivative would be positive as long as you're plugging in a number for h that's bigger than 27. Now, how is that helpful? And this is where those of us who are math jocks, like, we were kind of hoping that half of this garbage wasn't important. And I will say a little bit of it was redundant, but there's this little piece right here that you may have thought was kind of weird when you read it. It says the internal temperature of the potato is greater than 27 degrees for all times t greater than 0. So that means that that basically this second derivative is positive for all t values greater than 0. So if you look over here, if you look up here, that would mean that the graph of h is concave up all the way from t equaling 0 on. I think I'll exaggerate how concave up it is so it's a little more clear. So it's concave up, okay? So now let's just look at the picture then. If you found the equation of the tangent line at, I'll just go ahead and like draw a little more of it. If you found the equation of the tangent line at 0.91, and then we plugged 3 into it, that's how we got the 43. Since your graph is concave up from 0 and over, you could see that h of 3 should be higher than that 43 that we got. So I would say, if you want, you could say this yields that the graph of h of t is concave up for all t greater than or equal, not greater than, to greater than 0. Therefore, 43 degrees Celsius is an under approximation. There we go. And a comment, this statement right here and this little sentence are saying the exact same thing. So you would need to say something to this effect. You do not have to say it just like I did. But you wouldn't especially also have to turn it into a sentence. You could just go to the conclusion here. Okay. All right, my friends. Now let's move on to part C. Quite a few points available in part C. They don't always do it this way, but every once in a while you'll have a part, kind of the last part be where a lot of the points are, and that happened here. So for part C, did I lose my paper? I totally did. That's so funny. Anyway, sorry. Let me look up what the question was for part C. Okay, I don't know where I put it. All right, it says for t less than 10, an alternate model for the internal temperature of the potato at t minutes is the function g that satisfies the differential equation dg dt equals the opposite of the quantity g minus 27 to the 2/3, where g of t is measured in degrees Celsius and g of 0 is 91. Okay, let's see, find an expression for g of t based on the model. What's the internal temperature of the potato at time t equals 3? So many ways to go about this problem, so here's my version. I'm going to start by separating variables. At this stage, if they ask you to solve a differential equation, it means that you can separate the variables. If they ask you to approximate a differential equation, that's a different story. So I just multiplied by dt, and then I'm going to divide both sides. It's up to you what you want to do with that -1. I went ahead and just divided it over. It doesn't mean that you're wrong if you didn't. So that means that on the left side, I could think of it as multiplying by -1 over the quantity g minus 27 to the 2/3. I hope this is making sense as far as the algebra goes. So then these canceled, and then on the left side, I'm going to rewrite this right here as -1. Whoops, not even -1. I'm just going to say the opposite of g minus 27 to the -2/3 dg, and then on the right side I have dt. And then now that I've separated variables, I'm just going to integrate both sides. Remember that there's a 1 as your integrand on the right side. So let's get the easy one done first. The right side is equal to, I'll leave a little space here, is equal to t plus c1. On the left side, you could be careful about your u substitution, or you could do what I'm about to show in your head. The work is not required, just don't mess it up. But anyway, so let u equal the inside function, and then du is equal to dg. Sorry about that. So on the left side, you'd have the opposite of the integral of u to the -2/3 du. I guess I didn't need that big gap. Then you could just use the basic power rule for integrals on that. So you add 1 to -2/3, you get 1/3, and then you divide by 1/3. So you'd have negative u to the 1/3 divided by 1/3, technically plus a constant of integration, and then t plus c1 on the other side. On the left side, I'm going to flip and multiply, so I'd have -3. I'm going to write u to the 1/3 as the cube root of u, and I'm also going to back substitute, so I'd have g minus 27 in place of the u, and then on the right side, I have t plus c1. Okay, now they said that I need to get a function for g of t, so the next thing you'll see me try to do is isolate g. So I'm going to divide both sides by -3. On the left side, I now have the cube root of g minus 27. On the right side, I would write it as -t/3 plus, and a constant divided by -3, I would just call that a new constant. Oops, I already used C2, so maybe let's call it C3. There we go. Okay, next I'm going to cube root both sides. Still, I'm just trying to isolate g. So now I have g minus 27 is equal to the quantity -t/3 plus C3 cubed. Okay, next I'm going to add 27. So I will now have g as a function of time. So 27 plus -t/3 plus C3 cubed. All right, my friends. So this is considered your general solution, but we want a particular solution where we know what the constant is. So that's where we use the initial condition. Please remember, always, even if you're pretty sure you're screwing things up, use your initial condition in whatever version of crazy town you've got going on, because they always give you points just for plugging in 0 and 91 into something. It doesn't have to be something good. Anyway, so let's put 91 on the left side at the moment you put 0 in for t. So we would have 91 equals 27 plus -0/3 plus C3 cubed. Solving for C3, I would subtract the 27 over. On the right side, you have basically C3 cubed. You could always cube root, but I like just thinking like what cubed is 64, and so C3 would have to be 4. Okay, now that we know what C3 is, I could take it back up to where I had g of t solved for. I just didn't know what that was, and so g of t, the particular solution, would be 27 plus -t/3 plus 4 cubed. This is something they were looking for. I know if you look at the scoring guidelines, they have this just algebraically manipulated. We're both equally correct. And then the last thing they wanted you to, based on this model, say what the internal temperature would be when t is 3. So let's just do that. So 27 plus -3/3 plus 4 cubed would be 27 plus, that's 3 cubed, or 27. So 27 plus 27 more is 54. So according to this model, the temperature when t is 3 would be 54, and then I would put degrees Celsius on there, like so. All right, my friends, that is the infamous potato problem from 2017. I hope this helps, and I hope you get less insulting application problems on your test next week. Take care, everybody.